In this video, I want to talk about a combination of dynamics of machines as well as system dynamics or mechanical vibrations, whichever you want to call the topic for mass spring damper analysis. So the example I'm going to be working on is a simple door closer model that uses a mass and or a spring and a damper to close the door with an initial position to the door. So like I said, this is a combination of dynamics of machines as well as system dynamics, and we can modify the system parameters like the spring stiffness and everything else to see how it performs. And with that, let's start working on this example. I'm going to be modeling a 4-bar kind of like crank slider mechanism, and the slider is going to have a spring and a damper attached to it to close the door when it has been opened by an initial position. So to begin with, I'm going to come to world first, and first thing I want to do is apply the pause control. Again, a Windows update broke working model somehow, and so when I try to run some simulations, it just freezes. So I have this code that you can also copy if you have the same problem, and pause control, create a new condition and paste it here. This number 1 is the number of seconds it takes for working model to automatically pause the simulation. So I'm going to change it to 10 seconds so I have some time to see how my system is working. The next thing I want to do is to close or turn off gravity from world, go to gravity. I don't want any gravity in my system. And then I come to object and actually view, and let's go to workspace and turn on ruler and grid lines, so it gives me some guidance of where I'm putting my elements in the system. So with that, let's go and start creating a 4-bar crank slider linkage. I'm going to move things around so I can see where the 0.00 is. The 0.00 is around here, and I'm going to create a door first, starting from here and extending it to the sides. So this door, I can right click on the geometry and right click and click properties and determine the length and the width of the door. The length the height 0.4 is fine. I'm going to change the length or the width to 8. Actually, before doing that, let me pin this end so that it only shrinks from this end, from this side of the door. Now I can come back to geometry and change its, okay, so when I changed it, it decided to move. So I want to put the, all right, that makes sense. Okay, I want to put the pin right at the 0.00, which at this point is not. 0.0 is right here, so I have to move it further. Okay, so this would be the 0.0, and I think minus 0.2 in the y direction. That's okay. I can put the pin right there. So that's going to be how actually the hinge about which the door rotates. So while I'm making my model, I'm going to temporarily ground this link so it does not move anywhere. Then I'm going to create a slider, one of those door closers which incorporate a slider to move things around. So for the slider, I'm going to put it right about here-ish. Let's see. If I want to make sure that the door slider actually does what it has to be doing. So if I place a door slider about here, it should be fine. Let me pin it over here and change its dimension to, I want to change its width to 2, which is about right. And right now its y is at 1.5 and its x is at 3.7. That's okay. So let's see, the height is 0.6. I want to make it 0.5, and for that I want to pin it here and then change this to 0.5 so it only shrinks in the Okay, so 0.2 and 0.5 are the dimensions for this slider. And to make sure that this slider moves only in the horizontal direction, I'm going to apply slot joint on this end and this end. So make sure that it only follows a horizontal path. So I'm going to click here and then click this one again and right there. So if I try to move this, you can see that it moves only in the horizontal direction. So if I move it around, I see that, you know, right here, I think if I put it 4, this should be a good position for the slider. So again, temporarily, I'm going to block this or ground this so it doesn't move anymore. Actually, why is it moving? That's a good question. If I click on this again and let's see, ground here, and if I try to move it, to my surprise, it still moves. That shouldn't move, but I think we can deal with that. That's all right. So the other thing I have to do is to create a coupler between the slider and the door. So let's create a slider starting from there. That's fine. And then I'm gonna pin this end and then change its width by twice as much. So I'm just say times 2. So it goes that way. And then I'm gonna pin this end of it. Then if I rotate this coupler, no, about that point, about this point. Okay, let's see what happens if I change the height of this thing to about, let's say, 2 or 2.5. I think if I zoom in, that's a good point, reasonable point to pin the coupler to the door. If I zoom in, this is almost perfect. Let me rotate this a little bit so that we can get like here should be fine. Yeah, this is I think enough distance, and I can pin the coupler. At that point, I'm trying to snap a good point between the coupler and the door. Okay. So the other thing I want to do actually is to change the masses of these 3 components. So I'm going to change the mass of the door to 5, make it the more massive of my components, but change the mass of this coupler to 0.05 or 0.02. I'm going to change it to 0.05, and the mass of the slider to 0.01. So the more massive item in this system would be the door. That's what we expect. So the mass of the coupler is the slider is 0.01. The mass of the coupler is 0.05, and the mass of the door is 5. Before I move on, let me save this under documents. If I can find the documents here, working model, I'm going to call it door closer. And let's, for the sake of making this more visually appealing, change the appearance, make the door, I guess, orange, the coupler green, and the slider make it blue. Oh, actually, I probably didn't click properly. The slider should be, I'm going to call it blue for now. Next, I want to create a kind of like a frame or a wall to which the door will kind of like adhere. So I'm gonna start from here. Let's say this is enough space, enough position for the door, for the wall. For the wall, if I change the color to, let's say, gray or something, it doesn't matter about the width or the height or the mass, because what I'm going to be doing is permanently grounding the wall. so it does not move anywhere. It just stays where it is. Let me save this again, and before I move on, let me zoom out a little bit, close these for now, and I'm going to remove the grounds from the slider and the door, and see if I try to rotate the door. Okay, the door can move up to here but not much further. So let me undo this, and let me delete that link, and let's say if I can move this slider a little bit further to here, and now I want to pin the door and the coupler and try to rotate the door again. So this would be as far as the door would like to open. It won't open 90 degrees. So that's what happens when you try to design a door and or a system without proper dimensions. And so if I stick with this, I think that would be fine. Let me see. The maximum distance I can rotate this is right there. Right? And let me move it back to, let me undo this. And I can find, if I right click and get the properties, I can find, if I zero this for now, and when I rotate this to the maximum position it goes, say right, nope, not that, right there. Let's say this is the max that the door goes. So the maximum radian that we can get for this is minus, I'm gonna copy this, minus 0.94378. That's the maximum radius we can go in the open position. So I'm gonna try to undo this, and now I'm gonna apply a mass a spring and a damper system. So if I look at the left panel, I see a spring damper mechanism right here. If I click on that, and if I select a spring and a damper system, I can create one. So when I drew this, let me try again. When I draw this, the first point I click on is somewhere that snaps on the slider. That means one end of the mass, the spring damper, is connected to a mass, and then the other end, as long as it doesn't fall on a previously created block, would be on a ground. So this is the initial position, the equilibrium position of the mass and the spring and the damper system, right? This is the equilibrium length of the spring. So if I try to compress or stretch this system, it will want to go back to its equilibrium distance or length, which is the one that you can see right here. If I right click now and I say properties, I can see the K for the spring and the damping coefficient. So for this case, I want to change the damping, the stiffness coefficient to 25 and the damping coefficient to 100. I want to try a very over-damped system that doesn't smash the door to the frame. Let's save this, and then I'm gonna right click on the door, and here I think if I right click and I say define a control, I can define a initial rotation, initial position, initial velocities, and everything else. I want to define an initial rotation, and for this I want to paste the value that we had from before, but it seems like it does not want to. Okay, it goes only to the other direction. So here we have a problem which is solvable. So let me bring the calculator. So we had this as the angle that the initial position we want to give to the door. But the initial position on the initial rotation only receives positive values. So I'm gonna say what happens if I say 2 times pi. So I'm looking at this angle. I'm going to copy the entire thing as the positive value for the initial position. Let's see if I can paste anything in here. It does not like to get to that position. What if I... Yep. So what if I try to rotate this and see if that would count? It does not. Okay. So this is turning into a kind of a difficult situation that is typical when you're working with a working model that is kind of outdated and it does not sometimes want to cooperate as it should. So it does not even let me move this thing around. So this will gonna stay where it is, apparently. Okay. So the angle, again, was minus that. So I'm gonna paste that number, which now I can't paste anymore. So what happens if I rotate this again to right? Nope. Right there. And right now, okay, again, we have got this problem. Let me remove this thing. If it does remove, actually, that's another problem we've got. It does not want to delete this. Okay, I have to select like that. So try number 3. I want to bring the door to its initial position right there, minus 0.95. So minus 0.95 is where I want to put the door. So let me undo this. Okay, now it does not like to cooperate. 0. Save this. Not again here. I bring the calculator again. So 0.95 is the radian for the initial position or the initial rotation of the door. So if I multiply this by 800 and divide by pi, that would be 54.43 degrees. Right, so 54.43 degrees. I'm looking at the negative of this one, so 360 minus 54.43 would give me this angle. So that times pi divided by 880, that's 5.33 should be the initial position of this door. That's if working model wants to cooperate. Let's see if it does this time. So I'm gonna right click on this and go to define. Let me click on this again. For some reason it doesn't have the measure. So right click, rotation 5.33. Okay, so this is the initial position after after so many fights with working model. So to recap, we created a 4-bar linkage for a crank starter 4-bar linkage. which is actually like a rocker slider because it doesn't make a full rotation for the door. We have the coupler and this slider with very low masses. The door has the highest mass. We applied the stiffness and the damping coefficients for the spring mass system. And we applied an initial rotation for the door. So this is the max that this door can open because we didn't really have proper measurements for the distances. So this is not a perfect system. And we have this frame that would resemble a door or a frame that the or the wall of the frame that the door is gonna collapse on. So let me save this, and if I click run, I should see that the because we have compressed the system from its equilibrium length, it wants to push the door open or closed. Let's see what happens. And as you can see, it goes towards the frame and it slows down, and hopefully it will close. Let me click run again because we have a 10-second pause control. So it's closing and it's coming down pretty smoothly, right? So now it's closed and it should not be running anymore. So it's just gonna stay there. So let me, when WorkML stops the simulation, I'm gonna reset this, and I wanna click on the door and do the measurement and only the rotation of the door. So let me just keep it right here because the door is not gonna come this way anyway. Let me expand this and see what happens to the door as the door goes from this position to the frame. So I click run, and these angles are shown in radians. So the door goes there and pauses again for that because of that pause control that we defined after 10 seconds. So it is going, and it's going to slow down. And then if I click run again, as you can see, it is still doing the measurements, but now the door has reached the frame, and because it didn't have enough energy, the impact did not cause the door to slam and come back down, right? So we have a door mechanism, a door closer mechanism that can close the door. And one thing else I want to do, let me reset this, go to the world and change the accuracy so we have a better accuracy in our video, our calculations. Okay, this, and I'm going to run this again to get a better calculation or more accurate calculation. Again, after 10 seconds, it's going to stop. And then after 10 seconds, again, it's going to stop. And if you run for another 10 seconds, it's not going to run anymore. So it's just going to be a perfectly closed door after its initial position. So that you can, after you reset this, you can copy from edit and paste the data in Excel. Let's go to Excel. And then you can paste it in here. And you can plot this and change it as you wish, like I've explained in one of my previous videos. But one thing else I want to do is play with the properties of the spring and the damper in here. At one point, somebody told me that the door closer mechanism does not have a spring. And that made me pause because I was wondering if it does not have a spring, how would the door close? And I was under the impression that if there is no spring in a door closer mechanism, the door will never go back to its closed position. So I did some mathematical calculations. So I proved with math that there needs to be a spring in the system. But I want to show it here. What happens if we remove the spring? By removing it, I mean I'm going to make the spring constant 0. And I want to click run. And as you can see, the model is running because the data is being calculated, but the door is not moving. And that also explains that if you don't have a spring in this system, it will not close. So if anyone says that there is no spring in the door closer system, that's not true. So I'm going to reset this. Now let's go back to the spring mass damper system. change it to 25 as it was. Now let's see what happens if I decrease the damping coefficient. If I make my damping less than it is right now. I'm going to change it by a factor of 10. It was 100. I'm going to change it to 10, and I want to see what happens. Run. The door goes violently going to hit the frame, and it's going to make bounce backs and bounce back. This is probably an underdamped system. That's why it's going to keep doing this. And it goes back and forth. It has a lot of energy. It hits the door and it bounces back. So what happens if I change the damping to even less than that? It's going to be much more violent, as you can see here. It goes, hits, and it does not like to stop bouncing from the door. So let's switch the damping to what it was, 100, which was pretty overdamped. Now I want to change the stiffness from 25 to 50, make it a stiffer door. And now what happens this time? It's going back and it's losing its energy, but when it hits the frame, it wants to make some bounce back. But because of the high damping in the system, it doesn't do as much as before. If I reset this and let's change the damping for this system with high stiffness and 10 times less damping, let's see what happens. This case, again, we have a very violently closed door closer. So this is not a good door closer because the door wants to slam to the frame and just make bouncing systems. So as you can see in this example, the value of the spring and the value of the damping coefficient are very important in making a door closer that closes the door as smoothly as possible. I'm going to change these values again to what we had, and let's see once again, when you have proper values for your door closer system, that it loses energy as it's going back towards equilibrium position, and when it reaches the door, which in this case takes a bit longer than the more violent situations, it slows down and the door closing event happens very smoothly. That's what you want from a proper door closer. And right now it has stopped the door, but the calculations are going on. The other thing I want to do, maybe we can actually do this, is let's see if I can measure the forces applied to the door. If I can move this, as well as the total torque applied to the door. So let's see if these values change as I click run. As you can see, the total force changes, and also the total torque is changing based on the calculations, because we have a spring that's moving the door, so that we expect to happen anyway. Right. So one thing I want to do, just to show you what happens if we have very little damping in the system. I'm going to change it to let's say 5, a very little damping in the system. And what happens, I'm going to change the spring coefficient by twice as much. You see this slamming in every 10 seconds is going to create some very high torque and force in the system. Okay, I'm going to reset this. I'm going to copy this stuff that we calculated into Excel. Let me create a new sheet and paste everything. For the sake of this example, I'm just gonna plot the torque that is applied to the door. As you can see, at the 2 points, at the 2 times that the door slammed to the frame, we have very high torque applied to the door. And that's not a good idea. it could actually cause fractures or failures and catastrophic events over time. So we keep having these high torques applied, and probably that applies to the force as well. So if I let me remove these 3 rows, and then I want to copy column C and column F and see the forces. Again, you can see that the very high forces, it's like impulses applied to the door as it would slam to the frame. That's not something that we want in our system. So I'm going to delete these. And so we saw what happens in that case. So we looked at a system, a combination of dynamics of machines and system dynamics that correspond to a door closer system, a rocker slider system, and a spring mass or a spring damper system. We change the values for the spring and damping coefficients to see how that would affect the performance of the door closer. We saw how much force it would apply to the door when there is very little damping and high stiffness in the door closer. And we also saw that if you don't have a spring in your door closer system, the door will never close. It will stay at its initial position. So the idea that there is no damping in the system is not accurate, or there is no spring in the system is not accurate.